Hey, welcome to Coffee Compiler Club. Here today to talk about compilers or hotspot history or C1 versus C2 or SSA or not or whatever. Anything to do with compilers, language runtimes, prototyping, massive software development rewrite projects that do the entire JavaScript backend over again or anything like that. Everyone's recorded. We're going to be live on YouTube in a couple hours to a day. I didn't want to get to it. No set agenda, and we were just talking about why I thought C2, like C1 would never catch C2. So there's a little bit of history there. I joined Sun in like 96, the end, or 97 at the end. And then 6 months later, I started the C2 project, which was basically a redo clone of my grad student project, my PhD project. And in fact, the source code still mentions my name for the code that came from that. And C2 was well along and running. And there was a contingent of folks who had an earlier compiler, and C2 replaced it and did a great job. And they were not happy with how C2 worked, and they were darn determined to go produce a better compiler. And they named theirs C1 and named C2 C2. C2 wasn't C2 to me. It was the compiler. And in fact, I often called it Opto because I named the directory for my grad student days Opto for the optimizer portion. And that came over and it's still at Sun these days. The Opto directory has C2. Anyhow, um, somebody asked me something about it. I was like, sure, why not? It's a different price point. It'll never catch, but it'll be a cheaper, faster compiler, produce worse code quicker. And that's an
So,
interesting price
so
point.
yes, the question is when did you have the hunch that the framework that later became CF Nodes is better optimizing? Because I get that it's a graph, it's a more loosely, it's not that restrictive than the other frameworks, but you need to throw in like special interpretation, like scheduling the graph in order to become
Well, I've
the
known
latest.
this since student days.
Okay, but when you try it, when you try to experiment it, when you are sure or positive that this is the most general framework for optimizations.
Um, Grad student. So like I had done the C1 style thing already in my high school days. And I
Mm,
had done versions of it on and off before grad school at various other projects. I had this thing called Fifth, which was a fourth that had a GUI attached to it. And when I did code generation on it, it was very similar to a template stage, a level zero template jet, except with more optimizations between the pieces parts. And C1 was a further refinement along that stage. And I had seen other grad students make similar projects as well. And there was a fundamental lack of ability to do sort of large scale optimizations and large scale analysis in such a compiler.
mm,
So it put a hard cap on how much knowledge you had that you could then use to take advantage of do more things.
mm, mm.
Coupled with that, you got higher speed because you didn't flip IRs so often. You didn't change your
Okay.
IRs. You could do it in one IR instead of two.
Mm,
And so you also then typically went for a faster register allocator, where register allocation was always a big chunk of the compiler. And so
mm,
a linear scan allocator coupled with a one-shot IR pass and uh, not a whole lot of other optimizations possible on that structure. So they eventually added the loop things to it to do basic loop stuff, but they didn't have sort of the easy, cheesy, fast ways to go do a bunch of things. So you just don't bother. And that puts you at a price point where, roughly speaking, the compiler is 10 times faster than C2 and generates code that's 30% slower on an Intel and 50% slower on a Spark, which was the risk of choice at Sun,
mm, mm.
but 50% slower on all risks versus C2.
But because the graph is not restrictive at all, did you have a feeling that it's too loose in order to be bring back into the like mainstream framework for something
That
that you care
that
about.
was the learnings I got at Sun, and this was self-found because I was working with classic compiler guys with fixed placement. They had basic blocks and control flow graph, and you moved instructions around, and you did analyses to decide when you could. And SSA was a cool new thing, and it helped understand where things went and moved and how and why. But placement and scheduling was always a key part of any optimization you were doing.
Hmm.
And somewhere in there, I realized, like, why the fuck? No one cares if you do, X plus Y versus Y plus X and your global value numbering and whatever. None of these have any scheduling placement
Yeah,
constraints.
but let's say you have the general idea that the graph is the most general thing, but you now you have I need to get SSA semantics out. How do you bring that graph into SSA
Yeah,
semantics? What was the
no, it's
process?
the
What was the
right, right. It's the other way around. I'm starting with SSA semantics in my head. I'm sorry, program semantics in my head.
okay? Mm.
It's clearly a graph.
Mhm.
SSA puts a name to the feed function, and now I have
Okay.
a name to give to where values merge. That clarified and sharpened a bunch of things. So SSA was a great thing. Suddenly, I really have a graph. It's SSA form graph. I do this thing where I show people the alpha renaming to take you from a standard control flow graph and basic blocks and instructions. You've probably seen the paper then. And it's
Mhm.
just you rename things alpha, total, classic renaming, and suddenly you have a graph. Okay, now you've got a graph. Can you unwind the graph? So that was a problem to be solved. As a grad student in comp sci, I of course had graph, data
Is-
structures theory, graph theory.
So is it correct that the process was geared towards losing restrictions because there was too restrictive?
Yeah, the,
Uh,
the process in my head was most of the optimizations I do not need the restrictions for placement. Get rid of that restriction.
mm,
Oh, I have this loosey-goosey graph. Do I care? Well, I can do a bunch of cool things, but how do I turn it back into a program? Well,
yes.
that requires an unwind, but I just took these courses and they talked about graph theory and how to walk program graphs. Well, after you do a few of these things, the program graph walking becomes very obvious. All
Mhm.
the target strongly connected components, but we did all these other graph things. I could write this graph algorithm, and that was global code motion, and it was hardly a stretch over the other graph things. It was a mild reforming of other graph things that was just taught straight out. So once I had the in and the out, how far can I go on the inside? Well, okay, I can, do all the data things, but the control things look like graphs. I can make them graphs as well. I had to come up with semantics. I screwed around and vaguely came up with semantics that, like Petri net thing that shows up in the evaluator. Val 2 pays attention to that.
Mm,
I think Yasser's got an equivalent
mm,
C of nodes interpreter.
mhm.
Um, but at that point, I was like, I can do all the things the classic optimizers can do way the hell easier. And oh, look, I can fold control flow in. That makes that piece way the hell easier. And I was
Mm,
removing pass after pass after pass and saying, wait, I can fold this into the one pass. I can fold this into the one pass. So, sort of one at a time, I took 10, 15 different passes that people would do and folded them into my one big pass
mm, mm,
and got better optimizations overall and hugely faster. So from a performance, from the compiler performance perspective, it was as good as an, dash O2 compiler, but with the speed of the, dash go generate fast code without even debug info.
mm, mm, mm.
Um, While I was at Sun, I sorted out how to get the debug info put in place. That seemed straightforward after a bit. Actually, I knew that before I went to Sun, and it was Sun let me like go to town on it, and make it actually happen. Um, so that gives you, full optimizing compiler, full optimizing speed, and full debug info as well. You can stop and complete single step debug, and also go back to full optimizing compiler performance. And most of this stuff kind of coalesced when I was in grad school.
Mm, mm, mm.
The experience at Sun
Yeah.
was I put it into practice and made it work.
Uh, I was the other day or the other day before that, I was reviewing the Ben Titzer. I sorry if I butcher his name, the guy from V8. What
Oh,
he
Ben Titzer.
found,
Yeah,
Ben Titzer. Sorry
yeah.
if I
No.
which are
Good.
using it. So he said that it finds it hard the scheduling pass to in order to bring back
Yeah.
the semantics.
There were mistakes in my PhD,
Hmm.
omitted things that I didn't care about or I worked through and didn't matter that were more important in a industrial weight compiler that is in simple. So I went through it in Sun, realized that what I wrote in my PhD omitted some key things.
So
And
would you say that simple C of nodes interpretation, the simple is the really the C of nodes v2 or the best version of C of nodes?
it's not got a bunch of stuff that Sun's version has, but it's getting there. It could have it.
So I saw that loops are a big thing for the
It's
simple.
much more documented than the
Yes,
Sun version.
that's fine. And the process is really documented, yeah.
Yeah, yeah.
And yeah.
And I have to admit, I like some of the things that I did to clean up and the presentation. I like in the long run. Like I like my dense code. I like everything in one place. I like people to see what's going on, so I can see all the code in one spot. But there are some real easy to do separation of concerns that I could now do that I would require a full rewrite at Sun to go get. Um, Fine. Now, having said that, there's also some performance things you can get out of C++ that you can't get in Java that are kind of irking me. Like, I wish I could do this. I don't know how to do it. Um,
Something about pointers or
yeah. And allocation. You know, the main costs in a garbage collected language are almost always allocation.
mm.
You know, it's a bump pointer allocator is one clock cycle to allocate, and you're guaranteed a hard cache miss for every cache line you get.
So
And that cache miss runs you
is
out of
it
bandwidth, and that's your performance right there.
is it viable to become to come back to object pools in order
Yeah,
to
right.
not miss
So
allocate?
simple could do object pools. That would be a piece of it. One of the things I did at the Sun version, Sun C++ version, is we put in a word of flags. So we had a bunch of interesting features that you really want in the vtable. Like vtable's pointers to functions, but I want one of the vtable slots to have just a pile of constant.
Mm,
So I could do a virtual constant lookup and get, is this clonable? Is this a copy? Is this a control flow? Is this a memory? There's a bunch of Boolean tests. You put some bits
mm,
on. Fine,
mm.
whatever. Um, so instead you would burn a word per node, which inflates the node size, which goes right back to you're out of memory, so you bandwidth, you don't fit in your L1, so your compiler gets 10x slower because it's running out of L2, it's at L1.
So I see some experimentations about compiler that they represent all of their nodes by a long. So here
Yeah,
I
yeah,
believe that it may be made to work, but
yeah.
so their potential benefit there
Um,
just to
I fooled with that, and it's too small for industrial. Like
mm,
everything we do in simple right now, we could put into a long
mm,
for a node. So the node needs well actually you can't get the reverse edges easily. So a node needs an opcode. There are only like 50. So there's no more than a byte or 6 or 7 bits for
mm,
opcode. Okay. You need 0 to 3 forward pointers. And a forward pointer is 2 bytes if you allow yourself 65,000 nodes and you're just indexing them. So that's 6 bytes, one for the opcode, some extra bits floating around. You get 3 inputs. Okay. Well, not everything can be done with 3 inputs, so you have to give up on certain program shapes. Outputs
mm.
also have this property that they have a very exponential scale. So I guess you could do outputs with the second word. You need
But
0 to 3 outputs typically, probably one or two, except for occasional dudes will need hundreds.
But because everything is numbered, can we throw in like something like perfect hashing because it can squeeze all the numbering in
You
a very
need
little.
you need 65,000 unique nodes. Out of your
Mm,
16 bits for a node pointer, node index, you're going to use them all,
mm,
or you're going to blow out any mid-size compile.
mm, mm.
So larger compiles will still blow out 65,000. C2 hit that plenty. That's eventually we move C2 to a full 32-bit pointer because
But
16 bits, which was the earlier.
how far can we you assume how far can we go with 65,000, and you're assuming we can come up with a way easily switching,
Yeah, you
expanding
have
that
to
many.
separate build that has a double size pointer things. Yeah, so that's all your mid-size things. And certainly all your small compiles, and there are plenty of those. And
Mm,
most of your mid-size, it's a bigger compile. So some big function has some hot stuff that wants to get inline pretty big and pretty deep. Suddenly you blow it out.
mm,
So in the land of C2, the only fallback we had was you ran without C2, and this is before C1 or C2 were tiered. So you ran interpreted if you blew out C2.
mm.
So we were living with 16-bit node numbers, and compiles would fit easily in the L2s of the era and sometimes in the L1s of the era. And then something big would come along and you'd never get it compiled. It would run interpreted and you'd die like a pig. So people yelled and I gave up on my 16-bit, my
Mm.
precious, precious, you fit in L1, L2, and you get to L2 only.
So how noticeable was the difference in slowdown
Oh, I
in
haven't done
fitting?
timing, but I assume simple's like 10x slower.
Mm,
It's got the right algorithms, but the data structures are forced to be much larger. It's probably running compressed pointers. It's probably still 4 byte pointers, but like I'm using Java array list for my inputs and my outputs,
mm,
and not an inline array with an inline index. You get another indirection on all your inputs and all your outputs. You get a lot of slop on the input side, for which C2 knew that most of the nodes, like an add, has 3 inputs: the control, which won't get set till the end, and the 2 other inputs. Well, okay, so you just inline them. And now you don't have any indirection for them all.
mm,
And that's size, and size is speed. So if for a JIT, there's a speed issue. Now, for code quality, going to be roughly the same if we had roughly the same optimization. So we're missing all the loop things in simple. Fine. We don't have range checks or we'd be totally safe. And I want to put range checks in, but I have to have loops optimizations heading in because range checks will bite you hard in loops unless you have the loop optimizations to clean up the range checks.
mm, mm,
Um, we have a very lame inlining story, and we
mm,
have very small code base, so I don't have any giant wads of code to go, do things.
mm.
A lot of these things are all
Yeah,
statistics
so
driven.
inlining should be easy. It's just cloning the graph and inserting it on the call side.
It's the
Mm,
heuristic. The actual mechanism is easy. Yes, you clone the
mm,
graph and you stitch the ends together, and then you let the peoples clean out the endpoints, and then after
mm,
that it's inline, and then the peoples clean it up. It's all great.
mm,
Um, are we going to have subclassing? We're going to have
mm,
class for name. We're going to inline new or allow new things. So this is like, am I heading for a full-blown programming language with a real runtime, a
mm.
real managed runtime that would let me do multiple threads, multiple inlinings, multiple class for names, loading, things like that? All these things impact the optimizer directly. You have to pay attention as you get there. Fine.
So class for name is like supporting reflection or just
Eval,
adding new code
adding
in
new
class
code.
for name.
Yeah.
Yeah, okay.
Yeah. As soon as you have a subclassing and you add code, then the subclass has multiple targets. Maybe. Maybe it never
Maybe.
does. Maybe it does. When did the multiple target shelf? Well, class for name loads another target in. So I guess class hierarchy analysis will come in with, you'll go look at where you get your performance when you have subclassing. Class hierarchy analysis does this great, simple, easy job of most of the time people don't go crazy, crazy with their class hierarchies, and they turn around and
But
say,
that
"Ah,
has become from perspective from the from ahead of time optimization. So ahead of time compilation
yeah,
has become
right."
yeah.
As if you're ahead of time, you would say, this is never overridden. This method, virtual method, is never overridden. I know what the target is. It's a static call now. Oh, it's static call. I can inline, go to town.
Mm, mm,
So CHA does all kind of good things. If you class for name, you have to go back and you've used CHA and you class for name, load new class, you have to go back and revisit, recompile. And then one of my very long-term goals for here was to have a general purpose VM for people to do things that wasn't the Java virtual machine. So you had other choices. And then I could do other things that the JVM
mm.
has trouble doing right now because it was geared for what it was geared for. it's geared to run
Mhm.
Java. So there are some
So
things that are difficult to do.
to leave the door open for new explorations, not
Yeah, you
not
have to
only the
go right,
JVM
right. See,
semantics.
see what doors got closed or get closed, and can you leave them open? There is some issues. There's a lot of people who say, I want alternative dispatch rules. And then the single inheritance has a very efficient translation to dispatch. And
Um,
the alternative dispatch rules that most people come up with, say your Groovy or your JavaScript or whatever, do not have that nice cheap ass thing that also supports class for name and also supports whatever kind of optimization analysis. And so you
I'm all
can't
for
necessarily
single
rescue them
class.
every time.
I'm all for single class inheritance because you can done all pretty much all the things because multiple inheritance is just a
Right.
complication
I,
really.
I just saying, you talk to the JRuby guys and the JPython and whoever else, and they don't have these, and
Mm.
their rules are more difficult to optimize in the general case. And they have some special cases. And one of the things that Hotspot didn't allow for was high efficiency where it was possible with some sort of special case, but on the bailout, you went to some really generic case. And later came along in method handles and invoke dynamic and the like. And I looked at invoke dynamic and method handles and all the things they're doing. I'm like, there's such an easier way to do that whole thing. That just irks my soul to see you guys do this incredibly complicated, convoluted layers upon layers upon layers upon layers of translation and slow moving virtual field function call, slow moving
Mm.
function fields.
It's
Yeah.
incredible. Like, method handles took me like at least half the total time of making my VM because there's just so many cases and it's like really
Right,
confusing.
right. And when I heard them going on, and I went to the last Java Lang Summit I went to, I watched that going on. I was like, "Holy crap! You guys are really serious. This is ludicrous. Just make a slow-moving field optimization. If this field loads a function and no one's written to it, and the VM can totally track any writes to any field at really low cost. If no one's written to it, it hasn't changed. If it hasn't changed, it's the same function. You're going to load the function. You're going to call the function. Okay." Inline, go to town, optimize. Oh, the user decides he's going to change how his function dispatch goes because he's got some fancy logic. He does his fancy and then he writes the field. Boom, compiler, runtime detects field change, deop the code and reanalyze and re blah, 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 and go again. I just like, what are you doing? Fine.
Mm.
There are a lot of these things where people, that's not the only one. So people would come along and say, hey, we're doing this cool thing. And it directly impacts the compiler and it's directly impacted by the compiler. And we're not talking to Cliff Click. And then I look at what they did and I'm like, that's a loser solution. There's an easy one right over there. And they're like, we didn't talk to you. And I'm like, yeah, but why not? And they were like, because we're not going to talk to you. Okay. And
Mm.
then JVM DI gets shot down because it sucks, or JVM PI, and then they got a new one, TI or whatever. The third iteration came along of the TI, DI, PIs because the first two didn't talk to me and they did a stupid thing. We're going to do a thing that performance that impacts every possible compiler optimization, immediately defeating many of them and causing giant slowdowns, and then claim we're going to detect performance by first slowing everything by tenfold and then measuring. And I'm like, that is not how you detect performance. That is not how you do performance analysis. What the hell are you guys doing? All right, never mind. I'm ranting. Fine. So, history, C1, C2. I knew they wouldn't catch up. They haven't, they didn't. Fine, done. Then they eventually started Graal, which could catch up and apparently has. Oh, they're not apparently far enough ahead that Graal's in serious competition for being the new default, but they've had a long time, so they might get there. I don't know.
I have a question for you. Something that you mentioned a while back now. You mentioned that you figured out how to put debug info into the compiler.
Oh, you broke up right as you said the key thing.
Debug info. So I'm wondering
Oh
about
yeah,
how you put the debug info in.
but that's
So it's
safe
something that
points.
also would like to do, and probably would be nice and simple as well.
Okay, that's safe points. Okay,
Safe
okay.
points.
So the trick with debug info is you have to have an execution strategy for what the programmer believes they're writing that's debuggable. So if the programmer's writing C code, it's one execution strategy. And if they're writing Python, it's another. And if Lisp, it's another, and so on and so forth. In Java, that strategy is execute JVM bytecodes one at a time. Then there's a mapping table to convert it back to line numbers in the source code. And then IntelliJ and everybody, Eclipse, everybody runs the bytecodes one step at a time and does the mapping back to the source code. Okay. So how do you optimize and run bytecodes one at a time both? Well, you don't. So you run optimized with save points. Save points are a place that happens every roughly 1,000 bytecodes, 1,000 instructions, let's call it, where you stop and gather up the official architected machine state for the bytecodes. Or if you're in C, the architected state I would look at if I was looking at C code, and the same for looking at Lisp or whatever. And then having reached that point, you give it up and you go back to optimizing your code. So between 1,000 instructions, you're fully optimized. And you carefully arrange this around loops, and I'll talk about more about loops in a minute. You do a little more care at loops. But that does mean that every 1,000 clock cycles or so, you're at a save point. So if I'm running full speed in the optimized code and I hit the stop it now, then I run no more than 1,000 clocks, so no more than a microsecond. And then I hit a save point. Now I have a full mapping back to the machine architected state. You de-optimize.
Is that 1,000 optimized opcodes or 1,000 pre-optimized opcodes?
No, 1,000 post-instruction optimized. And it's rough. Sometimes it's 100 and sometimes it's 10,000. Statistically speaking, about 1,000.
Okay.
I remember
Is that why it's occasionally, sometimes I'm running something in Java and it goes into an infinite loop and I cannot break it?
Yeah.
Is that because it's all within one save point?
That would be almost surely a bug in the JVM DI spec communicating to the debugger. Okay. There was a time when, to keep the performance competitive with C and Fortran, I would not put save points in counted loops. So counted loops are very specifically ones that I know will terminate. So I have an upper bound and I have a stride on some index variable, and I say, you're going to terminate. So I'll pull all the save points out, but now you have no save points until the loop terminates. That could have been very slow. In practice, for what Java people wrote, it wasn't. But periodically, people did things where they did crazy, I'm going to run Mandelbrot's in a tight loop forever kind of thing, or I'm going to have 100 million whatevers. Fine. So eventually, we went to unroll and jam. So compile. I mentioned there's some optimizations did around save points on loops. You do unroll and jam. And so you get that save point every 1,000 clocks again. But the hot loop doing the hot work has no save points, but it has a short trip count. So it's unrolled by 4x or 16x, and then you SIMDIs and you vectorize and optimize crap. Okay, but then it's running some 100 iterations at the full optimized version. And then it stops, exits, save points, and then re-enters. So this loop is set to run 1,000,000. The inner set's running 1,000. The outer says it should have been 1,000,000, but it's actually 1,000 times and then 1,000 times 1,000, of which you get a save point every 1,000 times.
Is the save point something where you actually run through it even in the optimized code, or there's like an optional branch to get to the save point?
All of the above. So you need to check something to say, am I stopping for some reason? And that can be as cheap as a load compare branch of an L1 cache hit and perfectly predictable. So that can be half a clock to 1 clock, really fast. But you have to have enough state around that you could build up an interpreted version of things. So you sometimes have available or recompute values, or you have forced to spill things that you would otherwise declare dead and throw away in case they're loaded later. So there was a cost. The cost is generally really cheap. It's like I was forced to maintain this dead thing, so I spilled it to the stack once. So there's a store in the background outside of the loop, and I never cared ever again. And you test the bit. And if the bit flips and makes you go to a save point, then you run to some piece of code that grabs all the things, usually by having just a map, metadata floating off to the side. You do reverse PC, you look up in a hash table, you get a pile of metadata. The metadata says, I store the value here, and I put it here, and I store it here, and here, and here, and it's in registers, and this and that, and you find all the bits.
So
And
does
now
it mean that sometimes going into the safe point means you have to do a substantial amount of work to construct the state as it supposedly is?
yeah, it's not substantial, but it's non-zero. Like suppose I have in-registered an object and declared it dead. I don't ever allocate the object. The interpreter wants to have a real object. So, and the debugger wants to imagine a real object, but I never allocate any storage. So upon hitting the save point flag, I have to actually go make that object and then populate its fields and then hand it off to the interpreter.
Aren't there cases though when an object or something is dead, like it's in the interpreter state technically, but it's never used again?
Yeah. So we do an analysis of the interpreter's view of the world. This is really crazy things. You go down the rabbit hole even further and further.
I love
And
it.
we ask, will the interpreter ever care for this thing ever again? If the interpreter cares, we have to produce it.
And even if the interpreter doesn't, like if the user is breakpointing, they could actually like query that value.
So we went back and forth on this, and I don't know what the current state is. There was definitely a time where if we were going to come out into a safe point, but the object was known dead, we would just put a null there, but we had the fields available, but we didn't have the object for the debugger. And I think that was considered a no-no, and so we went ahead and allocated it. And so it was the interpreter would say dead, but if you could hit any bytecode and the bytecode could look at the thing, then we could reevaluate it.
I know V8 has gone with basically if it's very unlikely that this object could be detected, I guess in their case it's not really objects, or maybe it is, but they will actually drop out things like you will breakpoint at a very high point of the stack, and you can go back down towards the beginning, and at some point you start seeing like this very heavy loop I'm doing, or a very simple function. It doesn't actually see its parameters because those have already been kind of gotten rid of.
Yeah. I think we keep function call parameters specifically because people are excited, but internal local things, local variables that are dead, dead from the interpreter's point of view. Like the interpreter, like you always are able to press continue in the interpreter because people single step and it will never crash for single stepping yourself along. But yeah. So you have to decide what you're doing. In your case, Derek, you got one of two language sources, but I claimed the C++ is machine generated. That's not the language the developer's looking at.
Yeah, I agree. I was also thinking about like mapping back, generated opcodes to source lines,
Right.
And the variable names and stuff like that, which currently I'm not doing very well. Simple seems to do it a bit better.
Simple definitely tracks those. I give up tracking at some point, but I could track them. Like the parser has all that data.
Yeah. When I'm building the Python programs, I have these source location things, and they're like a thunk that if you execute it tells you everything about that place in the source file. But I'm not doing any of the work that sort of merge them together when I value a number.
So I have that location data in simple. So there's a place where you could add it in when we do the conversion. And then like the machine generated code, the assembly, human readable assembly dump can mostly pull out that location data and hand you pieces of lines where that opcode came from. And that might be very useful.
Yeah.
In fact, I suspect it would be very useful for us.
Yeah, exactly. So.
And along that, by the way, I have a lot of type info that I could also be dumping there. So you could say I have a load, and its load came from a structure, and the structure was the user called it the person object, and I'm pulling the age field out. And you could say, well, you're loading the age field from a person.
Mm-hmm. That would be useful.
About converting out to interpreter frames. So doesn't that mean that whenever you allocate a compiled frame, you need to make sure you have enough space to be able to convert it back to interpreter frames? Because I can imagine an optimized frame would need less, no?
So C2's like, I don't know, people know C2 makes very tiny. I graph color my stack slots spills. I have tiny frames. I
Right. Okay.
usually inline a lot of things. They inline fairly deep. The stack frame shrinks hugely. It's much smaller than the equivalent interpreter frames. So when somebody comes along and says, I want to deopt, quit executing this compiled code, it's no longer valid to execute this compiled code. The existing function call, so the compiled codes made a call down to some other frames, made some call. This frame is no good no more. I do not replace it in place yet. I'm going to wait till this unwinds to here, then the stack's all free, and then you pop this and rebuild and you get an interpreter set, interpreter frames down to here, but that was all free from below. So you don't care how small or big the interpreter frame to stack frame ratio is, because you're going to wait till you're at the frame that you're deopting, then you toss it and build the new frames. So, all right, so now
Okay. Couldn't you stack overflow though if you're like close to the end?
Stack Overflow is a separate thing, and Java is really perfect about Stack Overflow.
Good.
Fucking trouble to make it perfect, but it's really perfect. The only rule there is the exploded frames have to live within a C2's future Stack Overflow stack probing. So, and when a C2 frame enters, the general story is if the frame involved has nothing that exceeds 4K, including the exploded interpreter frames, then you don't have to do anything. But if you've inlined so much and your frame is so big that you're going to exceed 4K, you have to put a probe in and claim there's at least 4K ahead of you. And why 4K? Because that's one TLB small page. Okay. And then at the end of the stack frame, we've taken a guard page that's 4K. And if you touch the guard page, you're going to blow out and Stack Overflow. So C2 knows that when he enters a frame, there is at least a 4K after him, plus whatever he's got on the current page. And if he explodes in the middle, that'll unpack, and it may unpack into that 4K, but that's what that 4K is for. So it'll probe, say you're throwing a Stack Overflow, you unpack into the 4K. Now that you're in the middle of the last 4K and you cannot go again, you immediately throw Stack Overflow, which immediately unwinds. And so you reclaim a frame. Then the Stack Overflow guy looks and says, are you out of the guard page? No, you throw again and again and again until you're out of the guard page. Then he resets the guard page unless you run forward. Often you'll immediately throw again into the guard page. So these tests, they do things like run in a hot loop, this tiny thing until it starts to compile. And then C2 says, oh, it's just recursive. So I'm going to inline 10, 20, 40 frames, huge count. And the unwind would be huge count. And then I'm going to call recursively until I ran out of the stack. And then as I run out of the stack into Stack Overflow, I'm trying to set bits saying, this is my status when I threw, if I didn't throw, if I did throw. And the semantics of Stack Overflow are very special, and you want to catch it, right? The answer is, if you catch it, we allow you to catch if you're in the guard page, but the semantics are we can immediately throw again instantly, and you can't detect that you got caught and rethrown. So the semantics are you get caught and rethrown.
Oh, interesting. I didn't know that. I thought
But
you
you
could
can't
always
do anything or detect that you were in the
Okay.
guard page when you got rethrown until you come out of the guard page. Then you can execute some code, set a status bit saying, oh, I caught Stack Overflow, but you popped 17 frames, however many frames you popped to get back. So it's all very nitpicky and fiddly. And once you get into the zone where you can guard and unguard pages and you can count frame sizes and do these things, and it's no longer rocket science. It's just tedious bit fiddly shit. And you need hard tests that do stupid, crazy things, like I said, where they force C2 to get compiled, and then he inlines hugely and he jumps down the count. Like if you ran interpreted only, you could get 10,000 frames. You run C2, you get 100,000 frames. You can't just count stack frames, because if C2 compiles, you get a whole lot more, because Stack Overflow doesn't say how many frames are allowed or not. That's not part of the language spec. You just have to verify that if you catch a Stack Overflow, that if you want to execute something, it may immediately Stack Overflow anywhere in there. So you might get any count of bytecodes executed before you throw again. What you really get is up to the next safe point, and you will throw again.
Or maybe not use stacks at all, like,
No, people expected that. Like the alternative to no stacks is either no recursion, which has its own. A lot of people get mad about that one, or heap based, where you have infinite stack, and Stack Overflow just turns into out of memory because you run your heap out. You're executing, you're allocating new frames in the slate because you got a bug. The bug's not going to
Yeah,
stop because you ran out 2 megs of stack. You're going to run till you run out of heap.
yeah. I mean, in this last project, I used no stacks at all and just put it all on heap, like globally accessible heap from a single
Right,
register.
right, right.
And it's just so fast, and like it's so simple also, because like you don't have to pass the same data through like how many 40 stack
So,
frames over and
so
over again for the same
that's a
context
different
pointer, right?
story. It has nothing to do with Stack Overflow. You use a bunch
Oh,
of
sure,
globals to
sure.
pass, you do, and it can be
Yeah.
very fast, and it has its own issues with long-term maintenance on large projects. Small projects, I do globals all the time. That's separate from Stack Overflow. It has nothing to do
I
with Stack
mean,
Overflow.
a singleton is like also a global that's like,
Yeah, you get
it's
read-only singletons. That's a great thing for a global. I do that all the time too. A lot of people do. That's a great one.
yeah.
The issue with non-stacks or heap-based stacks is that when you write the bug, the failure mode is very slow and painful out of memory, as opposed to a pretty darn instant Stack Overflow. So it's a much easier to debug bug to take a Stack Overflow fault. And then nobody really expects you to have perfect behavior on Stack Overflow. It's like out of memory in that you expect to die. Fix your bug and go on with life.
I mean,
But
I think
Java spec was, and we got it perfect. Fine.
like I think like you could have like more than what current understanding of recursive programming style can support in a
Okay,
single stack
so
frame
Onat,
stack.
you're headed down the path where you're about to go argue against 100 years of solid mathematics, and you're
No,
not going to
no,
be correct.
I'm just saying like it's a single stack versus you could manage multiple stacks per iteration.
That it's not. As soon as we have multiple stacks, we're going to call it coroutines. And there are plenty of people who do good things with coroutines. Coroutines are a good thing, and Go routines with Go is coroutines from other languages.
I mean, what I'm saying
Java
is like
didn't go down
I,
that model, but
I can just dedicate a single register per stack, right?
yeah,
And that single register is like I can look like in the past 2 or 3 stacks, like 3 frames before or ahead, whatever. Like maybe I need to pass future information ahead from the like before the call is like what I mean is the current model is like
the current
is
model does
it's too
support
restrictive for no
does
reason at
support
all.
no. The current model is extremely cheap. Don't be confusing passing 1,000 things through registers with using a global environment variable or a set of globals. That those are unrelated to stacks.
Oh yeah, yeah, yeah. I was just saying, like all this complexity and like it's not, it's also too restrictive, and I
Okay,
think
so
I, I'm
again,
more
say
in
too
the.
restrictive. Everybody on the planet's been using stacks since the 50s and 60s, and it all works well for everybody. So it's not too restrictive. It's you have a special case for which you could do something different and it works better for you, but you're a special case.
I mean, it's all this context passed through multiple stack frames usually for the same like information over and over again,
But
just so for like locals and like
Onet, that
it was like
is
controversial when NASA published like, okay, we're not even allowing recursion. Like you can totally
okay,
write
Onet, hang on.
software that doesn't
Onet,
allow a
Onet, you're not.
recursion.
I'm gonna mute you in a second because you are running on unrelated things.
Okay, sorry.
Thank you. So whether or not you pass context via a global context, a functional context, or 1,000 split out pieces, these are all different programming language choices. They can be done differently by different people for different projects. They're unrelated to to nearly every language. Every language supports all 3 of those models pretty much directly. And it has nothing to do with stacks per se. Functions as a way to abbreviate, shrink concepts, code is a great thing. Functions include the mathematical version of functions, which implicitly carries a stack. And so the stack is very much implicit in the math where we derive all our functional sciences from, if you will. followed by the programming language theories all have this implicit stack, except in a handful of rare cases. So
Yeah.
once you have an implicit stack, you live with it, you have it, and then things happen after that. You do what you're gonna do with it, use it or not, however you want to do it. Hardware does a lot of things to support fast stack access. Stacks are cheap. They have default cheap behaviors baked into them in a lot of ways.
No, yeah, I mean it's just a register, a whole register that's already like you can use it as. I'm just using it for
How would you
calling.
support the case of multiple functions with calling, needing information within each other without stacks, using only one register? Or
If you don't do recursion, then this is what Fortran did back in the 50s and 60s. You don't need a stack if you don't do recursion. Every function just carries a link register back to the prior function, but you only have one per function. And then you don't, as long as you don't have any recursion, you're good. And this is a known, this has been a long time. As soon as you have recursion, you need a stack because you have an unbounded count of these things, and you have to have some way to put them.
You can cheat your way for a tail recursion, maybe, or
if you can do tail recursion. If I do a standard factorial, I don't get tail recursion.
Yeah, and so
I'm just saying non-tail recursion happens.
You need multiple stacks in order to, yes.
In language implementations, parsing is a classic example. I want recursion, and it's not tail recursion.
I'm not against call stack using for the return addresses that already I use it for, but I'm not using it for the local data part anymore for this new project. I'm just
and other people are not also. This is a common thing. Either it's stuck in globals, or I have a language that allows me to do cross stack frame access, which a lot of schemes and Lispy things do directly. You coulda, woulda, shoulda been able to do it in Java as well, but fine.
If you need recursion, and that's not usually the case most of the time. If you need recursion, then you can just say, I'm going to dedicate this one register for a stack, and then you can access that stack anywhere, right?
Yeah, but I think you're not looking at what it means to dedicate a register here. I'm going to have registers to. I have register machines. So if I stop and say I have quantum computing, life's all different. If I have a register machine, then the expectation is there is a register for getting at the stack, because every other thing, including the OS, says I called through the stack to get your function, who then called through another function of another project for libraries and shit. Who knows? So there is an expectation of a register burned there. Okay, that register it's not the cost of a normal register. It's the cost of the stack pointer register. And generally speaking, there's all kind of special shit going around the stack pointer register. Then in the case of System 5 ABIs and various Linuxes on x86, you want to burn a frame pointer. I don't like burning a frame pointer either. That is a register that back in the the 8086 days, I only had, you said 8, but you lost the stack pointer. Okay, you did. Now you have 7. You lose BP. Now you have 6. Okay, that's a giant chunk loss. So I didn't do frame pointers. Early hotspot, no frame pointers. In fact, I think current hotspots, no frame pointers.
Yeah, I mean, this last project I used my own fort and using just the assembler, right? It's 3.7 milliseconds for a single platform for the whole compile from scratch, everything. And it also includes like shaders and writing to the standard, like, you know, to the output, to the file output, not standard out. Like, you know, like multiple shaders also, not just a single shader. It's 4 milliseconds for an entire application.
Okay. You've switched topics completely into shaders. So let's bring it back to compilers. It's nothing to do with
I'll connect to compilers. Like, I programmed this whole thing in x64 assembler, and now I want to port to ARM64, right? And I'm thinking, like, you know, do I have to write the entire thing over again?
That's why there's compilers. So you can write the high-level language and pick your target.
Yeah, compilers are a lot of complexity, though, and also you
those
lose...
rewriting from scratch in a different assembler.
Well,
I think from history, it clears who won the battle. So
yeah,
between
well,
compilers and writing assembly.
All right.
yeah. I mean,
Let's move on.
Okay, so switching gears. So,
Let's switch gears here.
but
yeah, I was
what?
thinking like, what if
Oh,
I
no.
didn't use, for example, if I use like just a limited amount of registers that are like compatible between both x64 and ARM64, and like I have enough
Onad.
registers, like
Onad.
what's up?
Hang on. I want to switch topic. Although the can I handwrite assembly that I can just change register names between architectures is vaguely compiler related. But I want to change topics
It's
here.
a lot simpler than like what you call simple, and you don't pay
Okay,
for
Onad.
registers that you don't
Onad.
use. It's not like it doesn't cost you to
Onad.
not
All right,
use
I'm going to
it.
mute you.
So.
Okay.
Okay.
Yeah, simplicity is in the eye of the beholder, sir. I write compilers all the time. They're simple for me. I don't write shaders. They seem complicated to me. So that's different for different people. We'll walk away from that one. All right, Theodore, you were trying to ask a question.
So what's the status for the chapter 20, the register allocator?
Oh, what's the status of chapter 20? Yeah, the register allocator. It's down to call or call you save registers. I think no known bugs. This week I spent money on paying gig with Derek. It generates code that looks really reasonable for x86, ARM, and RISC-V. For pretty much everything, I do statistical analysis, spill code counting, and I'm getting roughly equivalent numbers across the 3 chips. There's likely to be bugs in the RISC-V and ARM register selection choices in places that haven't been sorted out until we get to encodings and run things on our simulator and have it crash and burn. We'll sort out at that time.
And so the abstractions are holding up against x86 and ARM, and what was the System 5 maybe?
System 5 and Win64. But like calling conventions in the C2 simple model here, the calling conventions are a trivial function you write. It's a 5 to 10 line function that parses the call signature and picks registers based on the signature argument types. So you can count floats and ints, and you can put them in the int float registers as appropriate, and you can run out a number so I have too many and put it on the stack. The key observation here is that because it's so cheap to change call conventions, you should change call conventions. You're calling pre-cooked library that's in System 5 ABI, well, you have to do that. Simple code calls simple code can have a different convention. Certainly C2 runs a convention for the interpreter, a convention for C2 to C2, and a convention for C2 to the C native ABI. And any of them can call any other one with a simple register shuffle. There's a shuffle maker, and then C2 itself will know what he's calling or who he's being called by and pick the appropriate convention. And then the register allocator just deals. So cool. That's the intended state. The current state is I don't have a call or callee save things lined up, but that's not very hard. So I'm hoping that it falls in this weekend. And then as far as I know, that's the end of chapter 20. There's endless room for spill heuristics. The spill heuristics I have things I could still fiddle with, but you have to let it go at some point without having a larger corpus of code to go compile against.
That was I'm about to say. So we need to test to gear it to the splitting and the auto heuristics in order to better register allocate. So
the splitting heuristics are overtuned for the code I have, and I need more code, but I don't have strings in a print. That's awaiting post encoding.
That was I'm saying. So we need a larger corpus in order to gear it toward the optimization.
Right. And in my mind, a larger corpus is waiting behind standard IO and strings, so printf, and then you can write more code. So in my head, there's no point in beating on the register allocator heuristics anymore until I can enable people to write library code and standard print, do sort of normal things, and then hopefully see larger code bases. And then we can argue our way back to saying, oh, we can improve the register allocator again. With Derek's project, which I'm
How do you know your register allocator is optimal even? Like,
I'm sorry.
how do you
No.
know?
Okay, Onet, wait, back up. This is some theory here, some hard theory here. The problem is NP complete. No allocator is optimal unless it's also stupendously slow. There are papers that people do stupendously slow things to get optimal. It's a few percentage points here and there. It's never worth it. There are places where it's worth it. That's not true, but it's really almost never worth it to be optimal. So you're not optimal. So the allocator is not optimal. Having said that, if the difference between optimal and not optimal is less than a fraction of a percent, mostly no one cares. So whatever. So now, what are you going to do with not optimal? You walk away from it and you say, okay, it's not optimal, but if it were optimal, I'd only get half a point. I can speed up my program a whole lot more if I burn my time and energy on optimizing the program structure itself rather than trying to scrape it out of the optimizer.
Right. Well, I mean, is there like interprocedural register passing in compilers, for instance?
Yeah. So done a number of different ways. In C2, you just inline like a mad dog. You inline like the devil. Like everything gets inline until you know you're going to have iCache blowout issues. Immediately, then everything both optimizes as a normal, I'm inline optimized, but also the register allocator treats it as a big Y. So effectively interprocedural. The next piece is the thing I just talked a minute ago where I can change calling conventions rather easily. I can change it on a function by function basis. And in fact, where I'm going to go with simple is it's going to register allocate interprocedurally across function borders directly as a single WOD. So you will get different calling conventions at every procedure already. Yes. So the answer to your question is yes.
There is something interesting you could do in a tracing JIT as opposed to method-based JIT. So there is a trick you play as assembly programmer that you often write your chain of functions that are going to be called so as to maintain the arguments passed through this chain of functions in one registers. And sometimes you have to write those functions twice because there's a different chains going through the call graph. As a tracing JIT compiler, you could actually make track of which registers have been used and just keep the values in those registers. But I'm not sure that's done in production compiler. I don't even know if PyPyJIT does something like that or not.
I'm intending to do that in simple. That is
cool.
Going to fall out in the wash sort of fairly directly here.
Even though you are doing a method-based JIT, right?
So simple's ahead of time right now, so no jet. But it's compiling multiple methods at once in one compilation unit, multiple methods, and they call each other. And what's the calling convention where they call each other? Well, right now it's using the default one, whichever you pass in, System 5 or Win64 or whatever. But there is a future version of things that says simple calls simple code. Then I'm going to use the whatever register got there first calling convention, and it'll all be treated as a one big WOD to be register allocated all together.
Interesting.
And it's assumed that the register allocator will generally do better as if the functions were inlined.
Yes, as if inline. Right. Not inlining optimizations. We're right. Yeah. Right. There's a live range for a value at a here's maybe an easy way to think about it. A function header in simple, the function header extends the region node, the merge point, and parameters extend phi nodes. So it's just a region with a bunch of feeds. And now you do register allocation like you do with phi nodes everywhere.
No, so it doesn't know that it's register allocating for a function because there is register allocating for the concept behind.
Yeah, for the future concept of doing interprocedural register allocation, it will just treat them like a phi node. And a call is a multi-way branch, multiple functions, and a function is a multi-way return from multiple people calling. These are all standard things the allocator deals with anyhow.
Okay. So we will phrase the function register allocation as a control flow allocation.
Yeah. Right. It'll be treated as control flow allocation. Yep.
Okay.
And to do that, I have to specifically track the link register. Talk about Fortran, you have the link register, it's the return address, the return PC.
Mhm.
Well, if you don't call yourself recursively, I only need one of those, and it can stay in a register the whole time, which the ARM and the RISC-V will do so. Now, the x86 puts it on the stack anyhow, but I'll track it on the stack as a stack slot register anyhow.
Okay.
So, yeah,
Cool.
it could turn into some really tight, nicely allocated code that's across all procedures directly. Yeah.
Cool.
So that is future. I want to get strings in place.
Mhm.
And in my head, strings are awaiting method calls and the fusion of arrays and structs.
So
And
how large of a chunk is the work for supporting method calls? So you have to track this pointer and
yeah, nothing more than syntax.
Uh,
The parser will see that it's a method call because you're calling it from inside of you're building it, you're defining the structure inside of a method. It'll hand you a hidden extra this argument and change the scope.
yeah. So that was my it will, when it sees that it's inside the class, it will automatically allocate the first argument for the function to be this pointer.
Yeah,
Okay.
and then
That's,
right, and then change your
cool.
scope to include the class.
Yeah,
so I claim it's not a huge deal. And then after method calls, a few structs and arrays, and then I have method calls on arrays. And then from there, I can get all the string manipulation things come out, come out in the wash.
Cool.
Or available. Fine.
Like, I think, in this last project, I just said, like, I'm going to have like 6 context registers, right, in x64, and like 8 temporary registers that are basically like free for all for functions to use for whatever. Actually, I use
call a save split. That's pretty normal.
Yeah, I guess. I don't know the compiler stuff. Like, it's too complex for my like grub brain, I guess. It's like it's a lot of complexity to think about in terms of like what does this register respond to.
Go to your interesting point. Like, we get that you don't get compilers, but you're doing a lot of code-gen things at a low level that compiler does at a low level. So there is some synergies between the two. Maybe learning something about how compilers work would give you a different view on the world.
Maybe I'm not like, I don't think that's like, there's a lot of performance wins to be had versus like writing assembler. With assembler,
it's not the performance win for writing assembler. It's the fact that you can switch from an x86 to an ARM to a RISC at the push of a button.
Yeah, I would like for my source code to be compilable across multiple targets. And I would like that, even if I given up like 5-10% performance or something like that.
You give up a little performance, and in exchange, you get other things. The other part of that, by the way, is that the high-level language gives you interesting guarantees about safety and correctness that you don't get out of assembly. That in turn means you write code that is correct sooner, and you have more time in your life to go make that code faster. So it has been my common observation over 40 years of programming that people who write mostly assembler lose performance to people who write high-level languages as soon as the problem gets beyond a certain size. At a very low size where I'm directly manipulating hardware things, I'm doing shaders or whatever. There's some wins there. As you start to get out of the codec space, you're not doing visual codecs or audio codecs or whatever. They spend so much time getting their code correct. This is especially true for like C guys. They get so much time spinning the code correct, getting the code correct, that they don't get time to go make it faster at a high level. And there are giant wins at high levels that you want to get.
May I also suggest a couple of other benefits of high-level languages? You cannot share code effectively using only an assembler. And if you're writing any number of assembly programs, your team will die, and I can tell you that.
I mean, you can share code very simply if you.
No, you can't. Not effectively. I can tell you from experience.
No, right. I lived the realm where the only assembly was the thing. You couldn't do it. And then high-level languages slowly started creeping in, and it was a giant jump in performance and ability to grow teams and have them do useful things.
Oh, sure. I totally think like, I don't think writing assembler is like easier. It's like, I mean, it gets easier,
Okay.
for me, it's,
Wait, Onet. I don't want to have
yeah.
this discussion because this is not a discussion I'm excited about. This is a
Why
discussion that got
not?
answered 40 years ago. I
Oh,
want to have a
come on.
discussion,
This
and then
is
I'm
like,
running this forum, so I'm going to leave aside the
so,
value in writing assembly. I admit it's there. I certainly write plenty of assembly myself because I have to, but it is not what I write all my things in. In fact,
I mean,
most of my things are not in assembly. So I want to talk about compilers.
I understand that,
Okay, thanks.
I think that you're missing the point for like,
Your view is interestingly out of the box, interestingly different. So it's good to hear it. But also, I want to talk more compiler things.
I once worked with a guy who insisted on using ed as his editor. You know the old lot, the old
I
like
used Ed. Oh my
yeah,
God.
yeah, yeah. I was like, I had to fire him. He was so useless.
He was
But
still
this
using
guy,
Ed Win. What?
he was using ed like ed.
What era was this? What? But you're not
It
that
was
old.
like not that long ago. I hired him briefly. He did okay in the interview. He started using ed. After 3 or 4 days, he accomplished nothing, and I fired him. And I feel like that is very similar to that's very similar to insisting on using a assembly all the time.
Yeah, forever. Yeah, but okay,
Sorry,
that's
sorry.
not.
Yeah.
no, it's
Yeah.
fine.
Had to get there.
It's funny.
Onat is like the
But
efficiency guy here. He doesn't really care about the big picture. He cares how fast his assembly can be. So it's that has a value on its own. But in the perspective for a compiler and programming language, assembly is not that interesting.
I mean, it's just so complex, guys. You just don't see it. Like assembly can be so simpler than compared to the complexity that you get with
the
compilers, because
complexity is.
compilers are not also bug free, right?
Onet.
There's always
Onet.
code,
Onet.
like
Sorry.
always.
Life
I
lesson
shouldn't have
here.
brought this back.
Yeah, Onet. The life lesson here is that everyone has their own powers, gifts, special abilities. And for me, compilers are not complicated. And most of the people on these calls and at Discord are of the opinion that they're trying to understand and they are achieving a greater understanding, and the compiler becomes less and less complicated for them as they start to understand how it works. So it is not the case that for everybody, the compiler is complicated.
Okay, I have a compiler question then for you. Like, for example, when in a for loop, for instance, at the loop end, you jump to the beginning, right? And the register mapping changes, so you cannot depend on the registers that you allocated, because like the registers that you enter the loop, and then
works.
I mean,
the register allocator builds a structure called a live range, which is a collection of all the things that are using the same value that therefore have to be in the same register. Things that come into the loop, things that flow through the loop, things that go out of the loop. If they're using the same value, whatever value means, it needs the same register. That's what the allocator is tracking. Okay, now he tracks it very efficiently, and he doesn't actually maintain the list of all the things that the register model. There's a way to do this, so fine. But he tracks live ranges, and eventually a live range becomes a register. But when the live range becomes a register, and you have instructions, a pile of instructions, and each instruction says, I take some live ranges in, I produce a live range out. And the next guy says, I take live ranges in, I produce a live range out. And then you fold the live ranges together, and you build what's called an interference graph, where multiple live ranges have to be live at the same time. And then they interfere, and they can't have the same register. And then you get that interference graph and use it to pick registers, or however it's done. For different people, it's different technologies. For graph coloring, it's done with graph coloring, but for linear scans, it's done a different way. But you build live ranges and you interfere, and then you decide, you can get this register and you can have that register. As soon as I pick that register for a live range, I've picked it for all the instructions for using it for that particular piece. So let me up-level this again. What I just said was, there's a problem that looks complicated until you see the answer. And once you see the answer, you realize it's not that complicated. It has some pieces to it, but so does writing assembly, and so does, cross-method register picking. There's some complexities, but it's not huge. It's solvable. It's understandable. It's achievable. The register allocation is achievable.
Yeah,
Now,
I mean,
you want to go into the details of how it's done? We can go into more on what a live range is and why it is.
yeah, I mean, I
So,
tried to.
are you considering to be convinced that the register allocation can do enough job as if it almost you write it in assembly on your own? So, are you convinced that?
I mean, the way that I write is like I have three registers that I use usually, or
Let me.
sometimes I need like some other registers that I'm going to keep around
Onat,
for some time.
would you be
You know,
willing to look at uh, a register allocation running in action, showing
sure,
you before and after?
of course. Thank you.
Okay,
Like
let's
that'd be
go
great.
run the simple test here. I will pull it together here. Hang on, and I'll share in a moment. I'm pulling things up here.
Like what I was thinking is like, I was thinking about this problem. I mean, I think about compilers too. It's just like they're too complex for like,
Hmm.
and I always realize like, oh my God, I'd be
I have
better off
I
just
have the
writing
hunch
assembly
that
instead,
you
Okay,
think that compilers are a waste of time, but maybe Cliff and some of us can convince you that
uh,
there is a value in that.
I gotta
No,
find
yeah,
this
there is value in it,
error
I think,
here.
for like,
Oh, share.
for a lot of reasons, but if it's too complex, then I just prefer
Okay,
the simpler solution.
let me see here if I can do something. Okay, so I'm gonna compile this piece of code. So this is simple. The language.
Can you
It's
zoom a
very.
little bit? Can you zoom a
I
little bit?
can. Yes. Sorry. How about that?
Yeah, really
Okay,
cool.
this is this thing we've seen from prior weeks. It's a square root. It's integer only. There's a float one I can also allocate for. It does Newton's method to get a square root, which starts with some value you want to take the square root of. That's your first guess. You run forever. You do a little bit of math. If you've next is guess, you found the square root because the product of this come to itself means you're there. And otherwise you set guess to next and you go. There is a loop carry dependency of guess equals next. So as a minimum, next and guess have to be live at the same time. But there's a bunch of temporaries involved in this kind of computation as well. So let me go run this through the register allocator. So I've stopped it at the pre the allocation, and I'll stop it post the allocation. And pre the allocation, I'm going to show you what I have for an IR. What's an IR? This is an internal representation. Let's see, this is a difficult window to slide around. Is this visible to people here?
Yeah.
Okay, so this form of the code is one in which every single thing represents an x86 machine code operation, except there's no registers assigned. And there's node numbers. And a node number refers uniquely to some other x86 instruction, except for fees. And fees come out of SSA form. A fee function is a pseudo function, a fake function, that represents places where values merge, in this case, at a loop header. So there's a 2 put in a register. There's a parameter x set to some node number. There's a guess, which is.
I have a question. Like, can you instead of fees, if you use if you use a variable to eliminate the fee,
Okay, yeah. So let's go the other way around. People used variables before fees, and the greatest single improvement in optimizing on all compilers in the last 40 years has been SSA form, which has a fee instead of variable. Much, much better optimizations and much easier optimizations. So it's the other way around. We took the variables and made them fees.
Interesting.
So
So
this is the variable for guess. It
okay,
says a fee because it wants to take an initial value for guess, which happens to be X, because in the original code, it was the first guess was X. Then there's some computation that happens, and the node 26 is the back edge. What comes around the back edge is this final divide. So the code here kind of tries to say, without any registers yet, take an original X divided by my guess. That's node 23 is equal to that's the guess value. Add the divide with the guess, divide it by 2. There's the 2 up here, and here's node 27 comes from the add. Now that I have this is my new guess. Compare it to next. If they're equal, I'm done. If they're not, I have to jump to loop 18, which is right up top. And node 26, which was the old guess, I'm sorry, the old next becomes the new guess. So this is the form I'm going to allocate on.
Right.
The original code has a copy. There is no way to write that original code without a copy. This SSA form has no copy because the fee function allows me to silently rename things and get rid of all my copies. So when I come out of the register allocator, I'm going to get a copy inserted as part of the register allocator intermediate's job. So starting from this point, I'm going to run one step in the allocator and build up what's called a live range. That live range that I build will have internal self-conflicts I'll be forced to spill. I'll go through a couple rounds of spilling and building live ranges. I'll get a graph that I can color. I'll color it. I'll get registers, and we'll have a post. So let me first go to the post and see what it looks like when the allocator's done here. I'm just going to run down to the next piece and pull that thing up again. And now I have registers involved. Let me see if I can stretch this window and get rid of the slide thing. Okay, so something up here says, I passed an original value in RDI. That's because the calling convention says first arg in RDI. That one's just pinned. There's no code for that. It's just pinned. Here's my code offsets, except I don't have any encoding, so they're just 1 byte. It's a lie. Encodings come later. This dump doesn't have encodings in them yet. Make a copy, put a 2 in a register. Oh, make another copy. I wanted 2 copies but this is the header and it doesn't do anytime spinning the loop, so I kind of don't care about copies there. From an
Do you eliminate?
Half a clock.
Do you eliminate those later, or
this is the eliminated version? So with some work, I could get rid of 1 more copy here. But given the time spent in this loop, and this loop actually needs 2 copies without a particular optimization that's outside the register allocator's point of view, I can't get rid of 2 copies. I have to have at least 1 copy in this loop. The float version, I believe, gets rid of the register, and the RISC and the ARM versions get rid of register. Here, the issue is div, add, and div all demand the first input and the output be the same.
Right.
And then in order to get rid of the extra register, I have to commute one of these operations without any other reason to figure out why it should be commuted. So somewhere in here, the guess is in REX. It got put here. And I put it in RDI to be, I leave it in RDI because I'm going to need the guess, but I make my starting value in racks. That comes from the original copy of the world. Divide the original by the guess. Add the original to guess. Divide by 2. See if I'm equal. If I'm equal, I jump and go again. If not, put the value in racks to get out and be done. This guy is not the better looking one. Because it's x86 needs to commute this guy. I'll run this again. I will not run again. I will just continue, and we'll see the same thing done on ARM or RISC. I think it's RISC-V next. So I just ran. This particular test runs all 3 of these RISC x86 ARM in a row. So it looks very similar because we make the assembly look similar. So no change in the pre-allocation version. So let's go look at the post-allocation version.
It's using like already what, 4 registers or 5?
So so that's x86, which because of the calling convention, well, x86 demands AX for divide and DX also is part of divide. So AX and DX are immediately consumed just to get the divide to go. And then you need other registers to hold the divide by 2, and you need a register to hold the original value because you need the original value for the entire loop, and so on and so forth.
Right.
So here, this particular guy, I hate the register names. I probably should change them. They're like temporaries and argument 0 and argument 1. So argument 0 is here on exit. So there's no move down here, and there's 1 less move in the body. So this one has two fewer copies, but key 1 less in the body. So some value for guess comes from the fallen for temp, which was the original A. You have to have a copy that's going to be preserving the guess. Then you can go say divide the original by guess to get the start of the next piece. Add next with guess, divide it by 2, compare, branch, and jump. So this code I grabbed because it's tricky to allocate for anybody, but it's small enough you can get it. I can pull up much larger examples for which you would be annoyed at trying to allocate for because they're so big. And that's the point of the allocator. It's just like, hey, here you go. And it's not terrible. The calling convention down here, it's missing some pieces. So it's doing a little bit of register cheating with the correct calling convention. It wouldn't add any copies. It just put things in different things. But put the argument to your temp so you can call it, so you can move it around squirt. It's an A0, you want it for squirt. You get a result in A0, you have to move it in a register because you're going to crush that for squirt again. And then you add the 2 as an argument for squirt for the second squirt call, and then he adds the 2 square results to return. So this is also pretty reasonably done. You can't get away with having fewer than 2 copies because squirt, until you know about calling conventions, because squirt thinks he's going to crush registers.
Right, yeah. I mean, the thing is,
and again,
sorry,
at the drop of a hat, here it is for the risk. I think I'm doing ARM. No, it's got to be the ARM version, maybe. It's probably the ARM version. And the same thing goes on here. I have to have 2 adder ops, so I'm losing. Divide must be 2 adders, so I have an extra copy in here without a commute. And otherwise, it's a reasonable allocation. Okay, so.
Yeah, sorry, I remembered. The thing is, like, for like most of the time, I think optimizing to that level for like cold code does not matter, right? We're talking like
Bing. Exactly.
less percentages and like, spanning all that compiler time for like that cold code.
That is the point of, it's there it is, Zoom hiding my things here. That is the point of a compiler. You get a decent job, quite a good one compared to hand assembly for free, for next to no effort. And then if you need to go assembly because you do things outside the language spec, like touch hardware registers, or in the case of hotspot, there's the generated code, but then there's all these little assembly stubs because I do stack frame rewriting and I can't get stack frame rewriting out of Java or C. That you have to go to assembly if you're going to rewrite your stack frames. And so you end up with assembly left and right and hither and yon.
Yeah.
We look at the flow version or something else, or some giant piles of code.
I have a feeling that I'm hearing an objection that so much effort put into the compiler is a waste when you could just hand assemble it when you don't care that much. Was that the argument that?
It's like assembly is already quite efficient because like you have all the registers all the time.
Okay, here's maybe the starting point. That's not what not the thing that you've got figured out yet. You said I have all the registers. Immediately you went to I have the most efficiency. That's not the important piece. The important piece is I have the functionality at all. I have Zoom. I have Windows. I have an operating system. I have games I play, and I have email. These are giant, large projects for which efficiency is almost never the key thing. There's a tiny piece of code for Zoom for video codec, and there are gigabytes of code that does not need that level of efficiency. But I would rather have Zoom than spend decades writing gigabytes of C code in assembly. So Zoom gets me Zoom, or gets me spreadsheets, or gets me every other thing that you ever think of that comes out of computer sort of instantly, quickly. And then occasionally I need to do things out of the language spec or with a higher performance metric, as video codecs being one of those.
So Onat, what is the largest program that you wrote in assembly, source of code lines, maybe?
I can show it to you. I just wrote it, finished writing it.
Just do a line count. Give me the line count.
Yeah, the line count.
4,000 lines of like Forge code, which
Let me go.
You can get far for with 4,000 lines, but you can get Zoom. So
you can't get Zoom.
so if you are waiting for the perfect assembly version, Zoom will be like a hundred or so. So it's at least it's you have to consider that there is a good trade-off between the computer registers and computer assembly execution time and human time, and You have to at least consider that. So of course you can maybe think a way that you can write pretty more efficient assembly, but in the global picture of the program, wouldn't it really that much matter if you don't have a product at all?
I think it gets easier because like you don't have to name your stuff like all the time, because like you have all the registers already, right? Like so.
No, I don't.
If you do functional programming, you don't have to name stuff much either. If that's something that bothers you.
I don't mind putting names on things because it helps me keep track of what the hell they are.
Yeah,
of course. As soon as I debug, I want names on everything. But
yeah,
sometimes
here's
I write
a variable
chunks of
hash.
functional code. But
geez, I want to know my hash code is a hash.
I mean, I could like say like bx is hash, okay, like, and then I could just.
But you just did it.
The other thing that we're missing here. The other thing that you're missing here
like hash all the time. I can just say bx is like the point, you know, like I
don't. Wait, let's say that
there's this amortization of like the effort that goes into the compiler over, you know, for any moderately successful language. You know, millions, billions, trillions of programs that are using that effort. So people put good effort into a compiler, but it's at a program level, it's like
I can put some numbers on that for the Java side that are legit.
Yeah, you know, which one?
4 to 5 million Java programmers every day for the last 25 years are using the Java compiler internally here. The one that Simple is based on, or whichever way you want to go there.
Yeah, I mean, you know,
those guys write code
assembly
that runs on.
So Onat, maybe that is not your cup of tea. Yeah, maybe this is not your cup of tea, but at least to consider that there is.
All right, let me back away. Let's not try to convince Onat of what he doesn't want to be convinced of.
No. I want to write a compiler actually, because like, you know, I want to make my language also accessible to regular people. And like, you know, I know that people won't want to write assembly, right? Although I think that it's not.
Onat?
You know, I used to be.
Okay. I'm gonna end this line of reasoning, which is about you defending yourself and us trying to convince you of something that's been obvious to everyone else on the planet for a long time, and that's not a useful discussion to be had.
Okay.
So at some point, you'll decide, or you won't, about how to change your mind or not, and that's up to you. And we talking to you isn't going to help that. So we should stop. And it's not actually very fun to watch. I mean, maybe it's fun to some people watch, but So I want to do things to do with compilers. No, it's not your fault in any way. And I appreciate the external viewpoint. There is this other view. And when in the 50s and 60s, so I was coding in the 60s and 70s, there were plenty of people that shared the view that you have. Don't get me wrong. I saw this boatloads, but I haven't seen it in 30 years. So I'm like, oh, that's wild. Okay, so let it go. I mean, I'm going to let it go. I want you to let the discussion go, and let's go look and see if we want to do anything else. I usually quit around 30 minutes from now because I go lunch. Do we want to go do anything else? In particular, if you want to talk more about register allocation, which is very specifically a piece of compiler that you were at least moderately curious about, I can go down that path. Or we can pivot and do something else.
Thanks. I mean, whatever you want to talk about. I was just thinking, like, you know. Anyway, thanks.
Okay, so I can do a little bit of discussion. I want to say it's a reveal of the allocator. I did one last week. It's the same kind of thing. But the point is to show that the allocator is accessible, but it's not your strong skill set. So it's very accessible for me. I'm trying to make it accessible to other people. There are certain things about the allocator that that were very useful with formal training.
I understand. For instance, like, you know, if you're trying to like pass, like if you have some register stored in a context stored in a register, and that register is going to be used as a argument, like in a C function, right? Then you need to pass that register into another register, or maybe to a local, or to something else. Like I'm thinking, like, what do you do when it blows up, right?
So,
in the simple case, it works. I know that, and I've written that case also. But in the complex case, when it blows up, then it's like, you know.
Can I propose a complete change of topic?
Yeah, I think so.
Go
yeah.
ahead.
Oh, no, you're justifying your point of
I'd
view.
like to, I'd like to hear a bit of discussion about the upcoming roadmap for Simple.
Yeah, okay. So register allocator is very near completion. Tommy's been working on the encoding side, which I believe he has the x86 fairly well done. And so after register allocation comes encoding. After encoding, I'm going to work on getting this run through the simulator. And at that point, I think we'll find a bunch of bugs that you can't detect easily without actually having something to run. So encoding bugs, register allocation bugs, basic block layout, simple, probably no more simple peeps. I think simple peeps got nailed pretty good. So it's going to be get the encodings in, register allocation done, integrate the encodings, integrate probably Quimu, whatever, some simulator, and verify that we can execute code reliably. After that, we have a couple pivot points. One is go to ELF files, become a ahead of time compiler, and you can run it on Godbolt and generate code. As I mentioned earlier, I badly want to get strings in so you can write high-level language versions of IO and printf and debugging things and whatever. And that in turn needs method calls and then fusing functions and arrays, which are all but fused anyhow. So that's together maybe one chapter worth of like parser hacks. Then there's probably a need for some basic library things to get enough stuff in there that there's a usable framework for people who want to write at a high level language for whatever reason. Like I never intentioned Simple as being a language you would write a lot of code in. It was a dumbass tutorial language whose only purpose in life was to inject nodes into a sea of nodes compiler. Along the way, it's cleaned up a bunch. It has a bunch of features I kind of like. I don't see any reason to keep. I think I should keep going with making it more usable, and that means it needs enough of a library of basic things that you can happily write local like array copy and printf and things like that. You want to some version of that needs to come through. Once that's there, these things are pivotable. If Untether is going to pay me to go do loop ops, then loop ops come sooner. That's fine. I think I want strings in IO, both of which, like I said, that's not that huge a thing, but it needs to happen. Okay, so finish RA, integrate encodings. Encodings are there. Debug encodings based on whatever simulator. Method oops and array fusion, that's strings. Basic string shit. Now I'm kind of open to any possible thing on the planet in whatever order. And that'll be whoever pushes and however they push.
How about Simple to be used as a JIT?
Yeah, right. So you get to the JIT step first. You come around and you say, I have code. I run it in a simulator. I'm JITting. I'm running code. Okay, if I run it from inside where I'm making the code in the first place, which is the Java VM, I have to make a native call on a byte array that I put together, but I can do that. You have to have a native call wrapper. These things are available. And then you can JIT simple code in Java and run it in the JVM. Okay, boom. But write it out to an ELF file format is a post JIT thing. First you get the bits. And then
so with the current technology, it wouldn't be too far to have a bytecode emitter to be emitted for.
That's a separate one. So then there is emit a format which is amenable to future optimization and reading in.
Yeah.
And that's like not the x86, right? Like ELF is gonna be I'm x86 or I'm writing out to RISC-V or whatever. Then there's a version that says I have another format.
Would emitting bytecode be pre or post optimization? Like, would you go, from parser straight into bytecode? Isn't that what Java does?
No. The Java C does that. He does a bunch of stuff to get his types correct because Java has complicated typings, but that's a typing thing. So no, I would say go to sea of nodes, I would actually go to, well, back in the day, I'd have done an 8/1632 register allocation. These days, I would do a 1632 register allocation and encode out the sea of nodes with basic blocks and loops and a baked in 16 register allocation, except the higher order bit can be masked for 16 or the higher order bit can be available for the 32. And then that format can be jitted into machine code at the speed faster than you can move bits between your L1 D cache and your L1 I cache. And so you have a format that you can read from disk and JIT instantly and run. And then you can decide you want to do other things just like Java. That's your bytecode format. It has a free, I can interpret this shit really fast. And then from there, I want to go throw it through an optimizer that, do inlining and cross-file inlining and stuff. There's a bunch of things you might do. But I would first take simple, run it through as just ideal node, so I haven't picked my target machine, give you an allocator that you can totally ignore, and just have simple nodes. But if you have an allocation and you're trying to generate machine code to run it immediately as a JIT style, then having an allocation in hand saves you from trying to do a bad allocation in your JIT up front. Now you can, like I said, you can convert that kind of a format into x86 that you're running or ARM or RISC at the speed at which you can get it from your iCache to your D cache to your iCache. And then if you wanted to have several libraries of code, you're going to cross compile between. The JIT gets you at least to the point where you're running it not between each other, but.
So wouldn't, if you do the allocation, wouldn't you have platform specific bytecode then?
No, I would do a generic allocation.
Okay.
And it's the JIT's job for the hardware target it's on to decide what to do with the generic allocation. Like, I'll admit that you have a stack pointer. I could possibly admit that you might have a requirement for a frame pointer, although that seems to be, people complain about, Matt in particular complains about no frame pointer hurting a bunch of tools, but that could do an allocation like 14 plus stack pointer, frame pointer, whatever.
So if you do an allocation and you say you assume you've got 32 registers and then you go onto a 16 register machine, like what good is that allocation?
It's a 16/32 allocation. If you leave the fifth bit up, it's a 32, and if you strip the fifth bit off, it's a 16. And in the 16, you need some extra copies and loads, and those are known to be tagged as this is what I need on the 16 and not on the 32. This was a thing that went around back in the day when Java was just coming up and the jitting was like, people were still figuring jitting out and was kind of amazing. And people were looking at Java bytecodes like, this is a really bad format. Oh, it's a terrible format, by the way. Java bytecodes, it's a horrific machine-independent format.
Agreed.
Okay, fine. Isn't there a better one? Yes. What can we do better? Well, one of the things you can do better is you can pre-allocate and do a power of 2 sized allocation for 8, 16, and 32 chips at those eras. No one has a 30 and 8 now. Fine. And then that saves you, because otherwise the jitting was, people talked about jitting Java bytecodes as what I would call a template stage 0 jit. You read the bytecode and you just lay out this equivalent assembly one after another. And then you fiddle out the borders because it's a stack bytecode. So you do stack unwind things or stack fusion things, but you lose out on all the like safety checks that are redundant. And C2 removes 90% of redundant safety checks, or 99%, depending on your count. Most redundant safety checks go away, and you get all high performance and full safety. Well, okay, the optimizer cleans all those safety checks out. That's great. Now emit a bytecode that is known to pass all the safety checks. So that's the other things, you put enough metadata in that you can confirm that you have all the safety checks passed, so that if somebody, evil hacker dude, wants to make a broken format, it will pass all the safety checks. So it won't crash the VM, but he writes whatever junky code he writes. You can at least force the hacker to go up level and not get you at the Java level. He has to get you at the, whatever cross-site scripting level of things. You open yourself up to a security hole somewhere else. Yes. So these things are all possible. Now,
don't you also open yourself up to sort of maliciously crafted bytecodes?
Yeah, that's been done Oh my God, Java got popular. Every hacker on the planet handed C2 maliciously crafted bytecodes. Same as JavaScript.
Right.
So Apo's nodding his head, yes. Same, I'm sure, as JavaScript. Maliciously crafted every possible way on the planet. And
Right.
C2 survives them all. Yes.
But then if you've got all the safety checks happening beforehand, that's great. But it's kind of like
No.
doing your safety
No.
checks on the client.
No.
No? Okay.
No. The bytecode format, so the bytecode format as written to disk. So it's a pile of bits on disk.
Yeah.
Before you declare it bytecodes, you run a proof on it that it doesn't violate any of the typing rules of bytecodes.
So the compiler is going to check the bytecode.
The loader
The
loads
JIT,
the bytecode.
the loader, yeah.
Yeah, the loader, yes.
Yeah.
He will run the safety check at load time.
Yeah,
and you want to have a safety
verification.
check.
There's like a whole step where it has to like scan all the bytecodes, make sure it's all typed correct.
Does the bytecode verifier?
Java bytecode's a verifier. And the disk time is way huger than the verification time. So you don't care about verification compared to disk. Same as network. The network is far slower than the verification phase. Fine. And verification is roughly the same speed as like getting it into your L1. And since you're going to generate code out of your L1 into your L1 iCache, the verifier essentially you're stalled on memory anyhow, bandwidth, whatever, latency. So more or less you can view the verifier as free if you put enough information in that he doesn't have to do any of the horrible, really bad things to verify.
I think modern security is like built on completely wrong foundations. So it should be like,
Okay.
if you could run assembly safely,
No, Onat, no, this is not a security forum.
Seriously.
We're going to give security up to the language level and stop there. And then after that, it's the next person's job to get security sorted out.
Well,
and not here, not on this forum. Take that discussion to a different forum.
No, we're talking about like validation because like
we're talking about language level verification when loading bits from disk. So hacked bits. An adversary makes the worst possible bits he can dream up, and he gets all the time in the universe to make all the worst bits. Can you verify those bits and make something that you can then execute that lives within the managed runtime framework of whatever safety needs? And the answer is yes, and it's been done before. Java is one example, but there are many. Okay, simple needs to do that in my head. That's a requirement. And that's not, I mean, I totally understand how to do it. Yes, there's some interesting theory involved. Not that hard. It'll happen. Fine.
Yeah, because like, in my language, for instance,
Nope.
No.
Nope.
Seriously.
Nope. Wrong forum. We're also running out of time, so we're gonna leave it at we can do this piece, and then we're gonna go to the next step, which is now that I have language level security, what next? Not on security. So
I would be very curious to think through approaches for jitting code that is running on our chip, if such a thing is even
it's totally possible
at all.
Yeah, it's absolutely possible.
Very limited in terms of how much memory you have.
Right.
You have like
there is but for your particular use case, because you have a lot of tiny functions with high trip count loops. In my head, one of the few things that you could get on the fly that you wouldn't get ahead of time would be dynamic trip counts telling you something special about this loop versus some other loop.
I think the main thing that you're going to learn is network latencies. So you've got this big system of lots and lots of little programs talking to each other. And so then there's a bunch of work that's done to predict latencies and then account for that. But I would assume that I think there might be approaches that you could like sort of account for those somehow.
Right.
But you have to make sure you don't deadlock the system in the process.
So the thing that you said there was there are these latencies that are unknown, and as soon as you say I have an unknown, you need to get that known, and that's profiling. And now you need to have a profiling runtime that sits alongside your hot kernels are running and counts things. and it counts latency to get things on the network, or it counts average execution time, or cycles spent in the matrix multiply unit who runs 64 clocks, or whatever you're going to collect stats on.
Yeah.
With stats in hand, you can make decisions that may involve code generation changes. So there's a step there. Like the journey that Hotspot went through to get to where it is actually fairly long. So there's a code generation that was quick compared to everyone else's at the time, but did a good enough job. Few percent slower execution time and 100 times faster to generate the code, like C2, 100 times LLVM speed. Fine. Then there was profile data, because you couldn't JIT everything. And the profile data got ever more complicated, and suddenly C2 was given an enormous amount of high quality profile data for which you can now reliably generate code that, I won't say beats, but it's at least extremely competitive with the best LLVM can do, because he has high quality profile data. And if you go talk to like Arthur, who's not here today, he'll tell you they spent a butt ton of effort getting that profile data over to LLVM, who can then now take advantage of it in their particular VM, but not in a general case. In your case, you don't have that profile data, even, I want to say, even statistically, even from a history of a corpus. And it would be useful in code generation.
We have some profile data. We can spend some time looking
Yeah,
at
I
it.
bet you have, yes, you have some.
Yeah, I think it's very limited, and the methods that we've had so far are limited by the slow compilation turnaround speed, and I think relatively slow simulation or inability to write code without basically using assembly, which prevents the building of tools that exist on the hardware.
Yeah.
So I think all of those things are being addressed. Like, I think we're addressing basically all of those limitations. And so things become possible. And I'm sort of be curious to sort of think through those.
I think a JIT is completely feasible. Well, certainly feasible on a Raspberry Pi. The first versions of Hotspot with C2 were run on machines with not much more memory than a modern Raspberry Pi. If your individual risks are lower, you have a bazillion of individual risks that are very much cheaper. So, but there is a thing that says we gather the stats, we run them off chip to a host. And the host, with his high performance x86, eats stats, regenerates code, and then relays out the chip. I think there's a strategy that might do quite well for you guys.
Yeah.
I'm happy to look at see what it would take to get a simple version, a running, self-hosted simple version running on the RISC chip. But you have a substandard RISC chip, and maybe it's not quite big enough to generate code from scratch the way C2 does. But you could certainly do templates where you have plug in the gap for numbers that are things like latency things that change trip counts. Or like I've done a lot of that kind of stuff in the Misty past. The big block of code has been carefully handcrafted, and there are holes where I'm going to plug in constants that say things.
Yeah. Well, maybe there's a version of the world where, I mean, it'd be interesting to discuss. Maybe I discuss it in person rather than on a YouTube video.
Boy, you broke up sound wise there.
Oh, sorry. I was just thinking maybe. We'll take a sort of detailed discussion offline, but I think it'd be interesting to think through a couple ideas as well.
Yeah. Well, I mean, I'm going to be probably hacking Untether this afternoon. I'm going to switch over to Simple on the weekend, but Untether. So if you want to call me, we can go talk through roadmaps and what we're doing and why.
Yeah.
Okay.
Cool.
All right. Any last questions, and not open-ended ones?
I just wanted to quickly say that I do have Simple working in the browser now. So I was thinking of creating a little visualizer with GraphViz and everything. And I was really curious if you thought there would be any visualizers for register allocation that might be kind of novel.
It's the same as like Simple doing visualizers on peepholes. In the moment for explaining to people these simple graphs, you get all the rich allocators, they all have simple graphs printed up. Clearly, they ran into some tool and they hand wrote a bunch of graphs. When I do a large scale allocation, the interconnected nature doesn't lend itself. I don't have a good example that helps me debug really. Instead, I get these ASCII prints. Occasionally, I annotate them with vertical bars for live ranges so I can see why these live ranges conflict or why this live range got so big. But other things, I'm still using ASCII dumps for debugging as it gets complicated. Going to a visualization of where you get, like the interference graph, it conflicts. It does. And then it's a very hard theory on, very straight up, very, very undeniable theory on how you color. So there's hardly any point to that one. And that one debugged within, the actual coloring of an interference graph debugged within a day. It was nothing. Building an interference graph occasionally had issues that I've now worked through. Building the live ranges, again, a few issues now worked through, might have helped, maybe not. What really comes around is when I do splits, I mean, always in every allocator, it's always how you do spilling. So as soon as I do spilling, it's always, there's an interesting issue of when do you spill and when do you not, and how much and how far do you go with it. And I don't know what the right graphical presentation there is.
What if you
There was
don't spill at
actually
all?
Okay,
What if
so
there
wait.
was
what if
actually
Okay, hang on. We have two people talking at once. Let me not do Onat, who's dominated conversation a bunch. Somebody else is
I was
asking a
saying like
question.
what if you don't spill and like
Onat, I'm saying not Onat, who's dominated the conversation a bunch. Somebody else was asking at the same time.
so I was going to mention that there was a library recently came out for Rust's borrow checker, and the borrow checker in a way has some similarities with a register allocator. It is it's not quite the same, but it has some similar properties. Basically, live ranges, and there was a visualizer program for the borrow checker, which basically has some kind of it annotates the source
Put a
code.
link in the doc,
Yeah.
and then we'll
Well,
go
but that
offline.
was kind
Look
of
at it.
looked fairly neat, at least.
Okay.
I think I saw what you're looking at. Yeah. I just think it's super cool. Sorry, go ahead.
No. I had nothing useful to say. I was gonna say it's been a long time. Maybe somebody's done something cool that I haven't seen yet. I'm all for it.
Yeah, I would just think it'd be cool to have like with simple be able to pull up their program and then like look at how like exactly what ranges each register is being assigned to and so forth.
I mean, I have when I do that dump that you saw on I get the live ranges, and then I didn't show you the live range version, but I have the live ranges, and I can pretty print individual ones. But if I have a big program, so little programs, it's easy, and graphs make sense. As soon as I pull up brainfuck as a test case, and the live ranges and the code stretches on page after page after page,
Impenetrable. Yeah.
right. Becomes harder to you kind of go from the theory side. You can't stare at it. Okay, I'll make one more attempt. So Onet, you're going to try to say something. Let's get, if you want.
Yeah, sure, thanks. I was saying like what if you don't spill at all, or like how do you decide when to spill or not spill? Because like
Okay, so wait, you answer the question. I'm going to answer it.
Okay.
So the first thing happens is I have more things that I want to use than I have registers. So I must spill. I have 10, 100,000, 100,000, like many more things than I have registers. I must spill. So when I say spill here, I mean I must use memory to hold these things at some point.
Okay.
Now, in the land of many high-level languages, Java especially, but others as well, there comes a point where to do multi-threading correct, loads from arbitrary memory are carefully tracked because that's part of the correctness of a multi-threaded program. Having loaded that value once, I'm not allowed to go back and reload from that same memory location again because it may have changed by another thread and the semantics would be wrong, be different, it would just be broken to do so. So now I've
Yeah.
loaded a value and I ran out of registers. I have to spill it. It has to go back to the stack somewhere. And that happens. So now I have things that I have private access to on my stack frame that I've spilled, and things that I've loaded up into registers. And now the juggling act begins. When do I keep in the register and when do I don't? And the allocator has a series of heuristics and a series of interesting rules about how he decides. That's a question about allocation we can go straight into really quickly. The obvious ones are hot loops, get registers. Things outside of hot loops, do not when you run out.
Right. And
And the first big assumption here, though, you have to eat, and you have to believe is that you will run out. You must believe that you have more things than you have registers.
yeah, sure. I mean, I have local variables for that as like,
Right.
not as a stack, but I know that it's local in the context that I'm like using it, which is like I made a video player that plays a lot of videos, so I can say like I'm gonna dedicate a register for a video everywhere, and like
The allocator
so
makes
that
those kind of decisions as well. He dedicates a register for a live range, which is not the same thing as what you're calling a local, but it's a thing that is how it comes out of the programming. And
yeah.
he says, this is the register for this piece. Like I was telling you in the guess and next in my little test Newton iterations, there's a
Oh yeah,
register
and
for
I
the
can
next and a
remap
register for the guess.
I can remap those too, like
Right.
if I want that to be a different register, that's
Yeah.
like easy. And like I want to keep manual like control of that
Yeah, no
instead of
problem.
like the compiler deciding for me. Like
So
it's easy.
a fun exercise here is to go take your mental model of how you want to do and how you think about these problems, and look at the interpreter for hotspot, for which on a dozen different machines we very carefully pick long-lived registers to represent the pointer for the bytecodes and the pointer
Yeah.
for the top of stack and the current top of stack value and something for the register and for the garbage collector and something for this and something for that. There is this game we play in specifically for registers in machine code for the interpreter, which is entirely written in hand-rolled machine code and entirely portable across, like I said, a dozen different platforms. It was,
Yeah.
it's the last big masterpiece of assembly that I've dealt with.
Yeah, I mean I do that stuff all the time, like
Right.
dedicate use like some like
Okay.
registers that I'm gonna use to like
I understand how to do large scale assembly programming as well. It's not an issue.
it's
I'm
simpler
interested in
in
compilers
most
these days,
cases.
and I
Like
want to let
and also
no
I have another idea, like
hang on,
there's
Odette, no, I'm at my limit. We're done. It's time out.
oh, that's a
You can
shame. I
come
have an
another
idea
time.
about like
You can come another time, and we'll have more discussions. But I do want to keep the focus on
you
how we're
have
going
like
to do this
200 or
with
300,
language
500
design and
virtual
compiler.
registers in hardware, right?
Okay, no, you didn't hear me. We're done. When I say we're done, I mean we're done. And then we're going to keep the conversation around language implementation design. And a big piece of that is compilers and garbage collectors and multi-threading and 1,000 library design, 1,000 other things. Assembly plays
Compilers
a
are
role.
oppressive.
Yeah, I
Compilers
know
are
you can unmute.
oppression.
If you're going to be rude about it, I will kick you.
No, I'm saying it in a
No, we're
like
done.
a joke.
No, yeah.
But seriously,
Okay.
compilers are like oppressive because like
Okay.
they decide.
You're off topic again. I'm going to kick you. Leave it. Anyone else? This is a problem with Onat in general. I know he has some interesting things and interesting point of views.
He's hard to steer, but
yeah, you're hard to steer,
work
Onat, and keeping on topic is tough. So we're done for today. There is another week, and a week after that, and a week after that. This has been going on for 5 years. You can always come again. All right.
Yeah, I guess like
Bye-bye.
I won't.
Thank you.